Hello everyone, welcome to this tutorial. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to predict precipitation values for the future using historical data and Sarimax model. This tutorial will be in Google Earth Engine platform using Python API programming. In this tutorial, you will learn how to do programming by connecting Earth Engine and Colab environment. At the end of this tutorial, you will learn how to predict the future or how to predict the years that you don't have data for. So at the end of this tutorial, you can see you can highlight actually the predicted precipitation values using Sarimax model. This tutorial is very simple and easy to use for your research and project, and I highly recommend for those of you who are interested to climatological data analysis. Let's make a new Colab environment, open a new tab, and go to the Colab environment and make a new notebook and start coding there. So now, once a new notebook created, you must make a connection between Earth Engine and Colab environment. So let's start with essential libraries that we need for this connection. For GEE, another popular Google Earth Engine library. Next one, import X as XR because we want to convert satellite image collection to the array structure for the analysis. So let's run a cell, and you can also rename the notebook you already created here. This is GEE 0019. For example, this is the code I usually use at the first of the tutorial names. So this is precipitation forecast tutorial. You can set any other name you prefer. So make another cell. In the next step, we need to actually call or install XEE library. The XEE is one of the newest libraries developed by Google that utilized to convert image collection in the Google Earth Engine into array structure that help us to apply various machine learning algorithm through the Python libraries. So first install XEE because it is not installed before, such as EE or GEE map. So project connected to your Earth Engine account. If you go to the Earth Engine account, for example here, there is a code editor. If you go to the code editor environment, you can see your account information in the corner up here. If you click on and go to project info, you will see the desired cloud project or a specific cloud project connected to your account. You must enter your own cloud project into the Colab environment, just like this. Back to the XEE library instruction. XEE library instruction is available on the net. Just open a browser, open a tab in a browser, on a browser, and type about Google Earth Engine and XEE. The first link actually connected you to this instruction on GitHub. So as you can see, there is an instruction on GitHub that's actually specifically detailed all steps you need to use for XEE library, and one of them is about the RL that should be added when you are making connection between Earth Engine and Colab. Then a new message popped up asking for permission to make this connection. Then you must select your account or Google account connected to the Earth Engine and click on continue. As you can see, the Earth Engine library created, the Earth Engine connection is made. From now on, we can utilize the Earth Engine and Python capabilities together in the Colab environment. That could be really, really beneficial for the data analysis. For example, now in the first step, I'm going to use Earth Engine capability to define the study area here. So now we need to make a map interface. We need a map interface in which allow us to select our region of interest. We can do this process using GEE map, already explained how to import it. So make a variable as map equals to or map sets to from GEE library call the map function with a particular base map. For example, the base map could be satellites. Let's run the map. After a few moments, you will have an interface. This is an Earth Engine capability that you are using in the Colab environment. You will have a user interface allows you to select your find region of interest. For example, in this tutorial, I'm gonna focus on my own country, Iran here. There is a rectangle tool or drawing tools available. You can select your region of interest. This tutorial can be used for all around the world, not limited or constrained to a particular region through the world. You can use this tutorial for your own region of interest, and there is no difference in running the code. Just one thing change is about the ROI or region of interest. The rectangle created, but we need the rectangle as a variable into the code. That's because we need to call it for the next step. So region of interest ROI sets to from the map select the last feature that is drawn and convert it into a geometry. Now we have a rectangle as a ROI in the code, and it is allow us to clip the satellite data based on the rectangle already called here. So in the next step, we need to call the precipitation data because we aim to predict, for example, precipitation variation for the future or for the years in which we don't have the data. So now make a new variable as collection sets to go to the Earth Engine and find Persian dataset. As you can see in the Earth Engine data catalog, you can find your Persian, you can find precipitation data here. Precipitation data, Persian model, 27 kilometer spatial resolution, available from 1983 to 2024. So through the Earth Engine snippet, you can bring this collection into the notebook environment, just like this. As there is only one band, no need to do selection for the target band because already the target band included as a single one. So make a filter date to span your data to the period of time you want to focus. Imagine, although this data is available until 2024, but imagine we want to actually call data from 2005 to 2024 and do the prediction for the rest of the years until 2030. For example, here, now I'm calling data from 2005 to 2024. It's around 20 or 19 years data is available for me, for example, and I'm going to use these 20 years to predict the future from 2024 to 2030. So let's run a code. Now we have an image collection called from the Earth Engine data catalog. In the next step, for the prediction or a further data analysis, it is better to convert your data into the Xarray structure. Actually, the Xarray or XEE library is a revolutionary library in the Earth Engine that allows us to use various kind of data analysis method for Earth Engine image collections because most of the algorithms, such as prediction algorithm, not already available in the Earth Engine environment. So So, but Python allows us to do this procedure thanks to XEE. So now a data set created. Now we want to convert the image collection into array structure using XEE. From the Xarray dataset, call open dataset like this, and the input data will be collect engine sets to EE, CRS or coordinate system will be EPSG 4326. This is a unique code we utilize for WGS84, a typical or common coordinate system in geospatial data geometry, or the region of interest is ROI or rectangle. This parameter is about the scale. The scale refers to the spatial resolution. The data spatial resolution is 27 kilometer, but here our data spatial resolution, we need to enter the spatial resolution based on degree units. 100 kilometer, actually 1 degree equals to 100 kilometers. So accordingly, 0.2 means 20 kilometer, 0.27 means 27 kilometer or 27,000 meters. So let's run a cell and the collection converting to a Xarray structure. Now you can print out the data set and see what is inside the data. Here we have a data limited to a longitude and latitude based on the ROI, and also we have around 7,000 precipitation values through the time, and here the data has a multidimensional structure. Actually, the Xarray converts your data to a multidimensional structure, separated time, longitude, and latitude, and also the variable. And you can see the period of time starting from 2005 to 2020, and also you can see the detailed information about latitude and longitude. Now let's make a preview from the region of interest to see how precipitation changes in your region. Could be really beneficial to get understanding about the range of precipitation and spatiotemporal pattern. So let's make average from the dataset. From the input dataset, I'm gonna get average through the time for each pixel. Let's run the cell, and after a few seconds you can see the average precipitation value through the time of for 19 years. Actually you can get average of each pixel precipitation that shows you how precipitation values change from one area to another area, or from one pixel to another pixel. I'm waiting to see the result. It takes a few seconds. You can see it's done after 30 seconds. Now, if you print the DS min, you will see the detailed information here. We don't have time anymore because now we have a single image, and time is meaningless here because the output here is the average through the time. So let's do the visualization. Get call ds min and select the variable that is precipitation and do the plot based on longitude and latitude, just like this. Outlier values set robust to true. So just like this. This is actually the average precipitation for the whole of the area. As you can see in the southwestern area, more precipitation and decreasing as we are going to lower latitude areas. So it could give us an insight about average daily precipitation in this region. This is an arid or semi-arid area. Some of area is arid and some of them is a little has a little precipitation, categorized as a semi-arid region in the world. And now if you want to see how actually which area has more seasonal variation, just you can calculate the variance in each pixel through the time. For example, now dataset variance equals to, from dataset calculate the variance through the time. Do the visualization for variance image again. Precipitation dot plot x equals to long, y equals to lat, set robust to true. So there it is. Let's run a code, and this is seasonal variations. Actually, higher variance means a higher seasonal variability of the precipitation in the region of the interest. Okay, after getting some insight, now I need to convert my data to the monthly precipitation for the 19 years to see how precipitation varies over 19 years with monthly frequency. Make a new cell and a new variable as monthly data. Monthly equals to, call the dataset and do the resampling, temporal resampling. Temporal dimension was time equals to the months, and then for precipitation we need to have the sum of the precipitation in each month. So let's run a code and monthly data created. As you can see, now we have 228 months data that ranges precipitation, sum of the precipitation values from January 2005 to December 2023. Okay, in the next step, actually, I'm gonna do the plot to see how monthly precipitation varies in this area. But it is better to select a point and do the plotting and monitoring based on that point values. If you go to the code editor, it is very easy to find a region of to find a point, latitude and longitude. Let me to remove the previous geometry here, but through the geometry tools here, the marker is available. Click on the marker and easily you can select a point in your region of interest. For example, I prefer to select a region in the actually southwest of Iran, where is actually a pool of agricultural area and also with with enough precipitation through the year. So as you can see here in the upper tab here, you can have access to the longitude and latitude. For example, from monthly data, I'm gonna actually select a point, select this point and follow and check its precipitation variation for time. Point equals to, from the monthly data, I'm gonna select a point based on its longitude and latitude. Just and latitude. There it is. It's very simple. I'm trying to explain everything with simple structure. The method for selecting the point is the nearest point or the nearest value to the location. Let's run, and now you will have a point location, actually this latitude and longitude, that shows precipitation monthly variation from 2005 to 2023. Now I'm gonna convert this into a data frame structure for a prediction purpose. For example, a data frame equals to point dot to data frame. There it is. Let's run, and a data frame created here. The data frame, as you remember, we had multi-dimensional structure: longitude, latitude, time, and precipitation. And now, from now on, you have that multi-dimensional structure, but in a data frame format. But here, the time and precipitation only matters because the latitude and longitude is the same, because we have a point and we don't have any change in the latitude and longitude. Here you can add precipitation as a target column. Precipitation, let's run. And now the data frame including two columns. The first one is time, that is index, and the next one is precipitation, the monthly precipitation based on millimeter unit. So now the data frame is created, and in the next step I'm gonna actually show you how to do this procedure, how to do plot the precipitation variation, the df dot plot, just like this, very easy. And you can see the monthly variation for this point, that you can see the PR values ranges from 0 to 175 millimeter per month. Okay, but it's only available until end of 2023, but we want to do the prediction from 23 to 2030. Okay, let's do this. If you go to the net and search about Sarimax model, you will find a lot of tutorials and a lot of links that actually explain the input arguments for this function. For example, here you can see that we can call this Sarimax model through the stats model.tsa. Hopefully this actually the stats model is one of the most popular libraries actually that in Python, that allows you to call the Sarimax easily without any challenge. So first state space or input, define a model first. As you can see, the AI assistant suggested the rest of the code, but I prefer to write myself because I wanna learn how to do this procedure, because sometimes AI assistant may not be available. So the input data for Sarimax model is our data frame. Order equals to like this, make a parenthesis. For example, I prefer to set all 1 because actually experimentally I got a good result for precipitation. Argument is the seasonal order, and here there is explanation about the seasonal order and 4 parameters available here to explain the seasonal variations. But I think among these arguments, the S or seasonality is the most important one. And again, I prefer to set 1 as a default value for the first 3, but the last one, seasonality, is the most important factor here. So the seasonality actually, as you can see, is the integer value that's explaining the number of periods in a season. For example, if you have yearly data, for example, if you have the monthly data, you will set, for example, 12. But here, if you set a 12, maybe the accuracy, maybe the output result not be very, very realistic. Let's start with 12 and see how seasonality may have effect on the output on the final result. Okay, the model is created. Another variable is result, in which the model fitted based on the data set where actually we created and parameters already settled. Okay, the result is ready, but result actually we need to from now on we want to do prediction. Now our model actually including information about how precipitation changes through the time and through the season. But from now on we want to do the forecast equals to from results get forecast called here. So the S here is very important. For example, I'm gonna do the forecast for 5 years. For 5 years, so 5 years, 12 months multiplied to each other. 5 years with monthly frequency. Let's run a forecast and then forecast dot, here as you can see, predicted mean will shows the predicted values from 2023 to 2000, from actually January 2024 to December 2028 for 5 years. Let's do the plot and see how precipitation varies in this period. Okay, now make another plot. The first, let's call the actually the first plot to see the variations before, because then we want to compare the future and before together and see if the prediction is realistic or not. So now the data frame dot plot, just like this, the same result we already seen, and the new result is the forecasted value, the predicted mean dot plots. Okay, but as you can see, the prediction is done, but the variation is not really realistic. According to the historical variations and such fluctuations, such kind of prediction is not very useful. But I realized that if you increase the seasonal order, for example, it shows that only 1 year actually seasonal variation considered here. For example, if you turn it to 2 years, for example, 24 months here, and train your model based on more seasonality or longer seasonality, then you may get a better result. As you can see, such actually new variations added. Okay, as we have, for example, 20 years, for example, I can, for example, set bigger values for this model. For example, imagine that for 10 years we will have 120 months. Okay, I'm gonna consider the 10 years seasonality here to train the model, because it is because higher accuracy expected in this scenario. As when you increase the seasonality in your actually the model, that definitely more times actually will consume by the for the analysis and something like that. So maybe a few minutes you need actually spend for the model training. I will pause the video in this period and then play it again. And remember that the code link is also available below this video on my YouTube channel in the description box. And if you face with any challenges, you can actually pick my code there from there and compares with your own code. And if problems still exist, feel free to reach me out and ask your questions. Here you can see there is a counter time that shows the executing time, and some, as I mentioned, actually takes more than 1 minute or a few minutes, but we can pause the video and see when it will be ready. Okay, as you can see here, after 5 minutes, the training model is over, and now if I run here, you will see actually more fluctuations added to the prediction values, because now I selected a longer period of time for training the model. So there it is. For example, you can actually select even a larger period of time for the predictions that may have influence on your output result. Okay, so here as you can see, this is our predictions, and also the prediction is done, and maybe you want to get export from the prediction values. For example, let's get output from prediction means to a CSV file, dot to CSV. There it is. And now we want to have it with a new name, PR precipitation values forecasted dot CSV with a CSV format. But remember to actually, let's run, see if it works. Yes, it works. Yeah. And go to the left panel, forecasted values available here. Double click shows the forecasted values. And if you want to if you want to download, just click download here and to have it as a separate file on your own system. Now you can open it up into the Excel, for example, Google Sheet I'm using here. Just go to the file and open, bring it up from your own desktop. So there it is. I'm gonna upload it. Go to the browse and PR forecasted, uploading here. So there it is. We have a date and predicted values for the next 5 years from January 24 to actually December 28. Even you can do the prediction for a longer period of time. It's totally up to you how to set the model parameters. For example, here, if you actually increase the steps to 10, definitely you will have prediction for the next 10 years. Let's try it again. For example, change it to 10. Now we want to do prediction for the next 10 years. And now you can see the prediction values for the next 10 years calculated. So if you think there is an offset in the values here, but it's true, it's returned to the seasonal order or any other parameters we added here. For example, if you reduce it a bit, definitely you will see the different fluctuations and different offsets in the output. It's totally up to you how to train the model. There are some methods on the net that allows you to figure it out how to train these models. Okay, for example, according to 36 months, maybe this one is a little bit more realistic. So such kind of actually parameters and working with this parameter, dealing with these factors allows us to actually get a better understanding about what is the best fit for our region of interest regarding to the historical variation. I hope you like this tutorial as much as I did, and feel free to use this tutorial for your own project. And if you had any questions or problem, feel free to put your comments on my YouTube channel. Thank you for your attention.